All right, welcome back to another fun-filled edition of Krueger's Calculus. We got ourselves a function here, and our goal is to find all discontinuities. We want to figure out where the discontinuities are happening, as well as the type of discontinuity. So, what we want to first roll through real quick are the types of discontinuities. There are four types. There's infinite, there is removable, there's oscillating, and there's a jump discontinuity. As far as oscillating is concerned, never going to have it. We're not going to see it. They're very, very specialized cases, so we don't have to worry about that. So we have the other three. The jump discontinuities will happen when we have a piecewise defined function, and hey, we have a piecewise defined function, so we have the potential. It's not automatic. We have the potential to have a jump discontinuity here. Otherwise, the removable and the infinite, those come from dividing by zero, the times when our function's not going to exist. So we can do any of those that we want to deal with first. I'm going to go ahead and deal with the removable and the infinite first. So when I'm dealing with that, I need to look at each individual piece. So first I'm going to start with this top piece here. I'm going to start with the 5 divided by x. 5 divided by x could end up dividing by 0. So what I need to do is find out when that happens, which is kind of obvious. We can easily see that at x equals 0, we would be dividing by 0. The other thing I got to pay attention to when it comes to piecewise defined functions is 0 allowed for this piece 5 over x? And sure enough, if we look at the definition for the piecewise defined function, that says to use that function when x is less than 1, 0 is less than 1, and since 0 would be plugged in and make that undefined, 0 is going to be a discontinuous point. So I know that at x equals 0, I have a discontinuity. So now it's up to me to figure out what kind of discontinuity we have at x equals 0. So to do that, what I need to do is figure out whether x equals 0 is a removable or whether it's infinite. How do we do that? Well, if it's infinite, it's going to be a vertical asymptote. So we have to do what we normally do with vertical asymptotes, which is look at the limit as x approaches 0 and see if that's going to be infinity or if that's going to be a number. So if I look at the limit as x approaches 0 of the function that I'm looking at right now, which is 5 over x, to evaluate that limit, we look at the y value at x equaling 0. When I plug in 0, I get 5 divided by 0. 5 divided by 0 we can't do. We know we can't do that, but we know what that approaches. We said that before in section 2.2. That is going to approach either positive infinity or negative infinity. It doesn't really matter. I don't need to figure out which one. We could try, but it doesn't matter at all. The fact that it approaches infinity means that that's a vertical asymptote. So at x equals 0, we have a discontinuity. Not only do we have a discontinuity, but at x equals 0, we now know the type of discontinuity. X equals 0 is discontinuous. It is specifically an infinite discontinuity. Why is it an infinite discontinuity? Because at x equals 0, we have a vertical asymptote. And vertical asymptotes go to infinity or negative infinity. So there's our first answer. At x equals 0, we have an infinite discontinuity. Next, I don't have any other points that would make a denominator equal to 0, so I don't have any other infinite discontinuities. I also definitely do not have any removable discontinuities. So now it comes down to the breakpoint. Now it comes down to, do we have a jump discontinuity or not? To figure out if that breakpoint at x equals 0, to figure out if that breakpoint is a discontinuity or not, at x equals 1, to figure out if that's a discontinuity or not, what I need to do is I need to look at two separate one-sided limits. I need to look at the limit as x approaches 1, and then I need to look at the limit as x approaches 1 from the right side. So, first, the limit as x approaches 1 from the left. So to do the limit as x approaches 1 from the left, I need to be plugging in numbers that are just slightly less than 1. That's what it means to be doing the limit as x approaches 1 from the left. So if I'm going to be less than 1, 0.95, 0.96, 0.97, I would be using this piece. It has no bearing on the fact that x is less than or equal to 1. That doesn't matter. It's the fact that just x is less than 1 means I'm going to be using the 5 over x piece. So the limit as x approaches 1 from the left of my function 5 over x means I plug in 1 for x into that piece, and I get 5. That tells me nothing. That is simply something that I'm going to put on hold. I have this 5, I know about this 5, but I just hold on to it because I also need to look at the limit as x approaches 1 from the right. So the limit as x approaches 1 from the right-hand side would mean I'm plugging in numbers a little bigger than 1, 1.4, 1.3, 1.2. All the numbers that are bigger than 1 will be using this piece, x squared plus 2, because it says x is greater than 1. I know it doesn't say x is equal to 1, but that's okay. I'm doing a limit here. I'm not doing the function value at 1. I'm questioning what the y value is approaching as x approaches 1 from numbers that are bigger than 1. So I'm going to go ahead and plug in 1 into that function, which is going to give me 1 squared plus 2. 1 squared is 1. 1 plus 2 is 3. Now I have enough information to determine if I have a jump discontinuity or not. The limit from the left was 5. The limit from the right was 3. Those are not the same number. If they were the same number, the limit as x approaches 1 would be whatever that number is. Say they were both 5. But it's not. One's a 5 and one's a 3. What that means, from what we learned back in section 2.1, is that if I asked what's the limit as x approaches 1 of f of x, that's going to be does not exist. And since that limit does not exist, that means we have a discontinuity. We definitely have a jump discontinuity. And so we just need to state that as well. At x equals 1, we have another discontinuity. This one did not come from dividing by 0. This discontinuous point came from a piecewise defined function, came from a breakpoint, and therefore this is a jump discontinuity. So we have our infinite discontinuity from having a vertical asymptote. We have a jump discontinuity because of the piecewise defined function. There's nothing else. There's no other points where we divide by 0. There's no other breakpoints. We're good to go. Discontinuities at x equals 0 and at x equals 1.